Jay Will After Dark is back. Nick Howard's here. Anyone else here? Oh, there you all are. 16. Great. Sorry about that, everybody. Hey, Richard. We'll see if this works better. There weren't a whole lot of real options for changing the settings. Hey, Samantha. Looks like everyone worked it out, though. Yeah, I might have to go to a different provider besides just doing the YouTube thing. There's other options. Okay. There's no point whining about it, Ben. It is what it is. I'll probably be tired at 9. Why don't we keep doing it? The next one's another sine graph. It also has a phase shift. It also has an amplitude shift. It looks like it doesn't have a vertical shift. Do you want me to graph another sine graph, or should we do something else? I mean, the problems take as long as they take. If you guys had spent some time already doing this problem set and knew where you had questions, it would be a different story. But if you haven't spent any time on it, then you don't have any questions to ask me. Move on, says Lauren. Fair enough. So the next one that's not just graphing a sine graph is merry-go-rounds. Number 90. A neighborhood carnival has a merry-go-round whose radius is 25 feet. If the time for one revolution is 30 seconds, how fast is the merry-go-round going? Okay, so I've got a merry-go-round, and its radius is 25 feet, and one revolution is 30 seconds. So it takes 30 seconds to go like this. So we first want to know, you don't like the Ferris wheels? Ferris wheels are great. What's the circumference? Circumference equals 2 pi times the radius. So in this case, circumference equals 2 pi times 25 feet. So circumference here equals 50 pi feet. And that's our distance. So speed, the linear velocity, equals 50 pi feet over 30 seconds. And calculator? So 5.24 feet per second. If we wanted to get omega, the angular velocity, we could say it's 2 pi radians in 30 seconds. So 0.21 radians per second. Any questions on number 90? Richard says next.
Fair enough. Sounds good. Let's do it.
The radius of each wheel of a car is 16 inches. This is number 92. At how many revolutions per minute should a spin balancer be set to balance the tires at a speed of 90 miles per hour? So we want to go 90 miles per hour. And we want to convert that. We want to convert that into revolutions per minute for a 16-inch or 16-inch radius wheel. So if the wheel is 16 inches, then the circumference, which still equals 2 pi times the radius, equals 2 pi times 16 inches, equals 32 pi inches. So when the wheel turns over once, we go 100.53 inches. And now I need to know how many revolutions per minute will make 90 miles per hour. So 90 miles per in 1 hour. And I need to convert this into minutes, and I want inches in the end. So if I times by times 1 hour is 60 minutes. Equals 90 miles in 60 minutes. And then I can say times 5,280 feet in 1 mile. So I've got 90 times 5,280 over 60 in feet per minute, and then times 12 inches in 1 foot. So 90 times 5,280 times 12 over 60 is 9,540 inches per minute. And if I go 100.53 inches, so I'm going to take all of this and divide it by my 32 pi. So 945 revolutions per minute. questions on 92? Input from others besides Richard. Though I appreciate your quick response, Richard. Richard of the fast internet. Okie doke. Let's do it. Oh, this is a really good one. This one's totally on our final exam. We should do this one. Monthly temperatures. So we got some data, and we need to fit a function. So I'm going to say this is definitely a Desmos problem. So I'm going to plug this into a table. And I've got 1, 51, 2, 55, 3, 63, 4. Let's see, 4 was 67. Uh-oh, we're frozen? Okay, let me pull off. Uh-oh. Just kidding. Frozen up. Okay, I think we're going to be back here in just a second. Now unfrozen. There we go. Okay, we're back. All I've done so far is added this data right here to this table. So I'm adding 577, 686, 790, 890, 984, 1071, 1115, 1159, and 1252. Cool. So here I've got all my data in this cool table, and we can see it makes a nice looking sine curve. And I've done A, I drew a scatter diagram. Now I'm going to find a function that fits this. And we're going to draw it on the diagram. I'm on 95, Sophia. 95. So here's my beautiful scatter plot. And now we want to say, how can we get y equals a sine of bx minus c plus d to fit? So clearly I need a greater amplitude. Let's see, the amplitude data goes from 51 to 90 or thereabouts. I'm going to call it 50 to 90, so 20. I'm going to say A equals 20. There we go. And then I can see that one period takes me 12. So I know that's going to be pi over 6. 2 pi over 12 is pi over 6. That's looking better. And let's see, the midline here is going to be about 70. Looking pretty good. And now I need to move it over. How does that look? Fit-wise, 2.4? Oscar, if you're going to foment rebellion during my live stream, then I'm just going to turn it off and you can foment rebellion by yourself. Ben, strikes work because owners of factories need workers to make money. I don't need you to make money. You can all fail. Anyway, there we go. I got to send this little function to fit the graph. Questions? It doesn't have to fit exactly. That's not what I'm looking for. How did I get 20? That's an excellent question, Sophia. Sophia, I noticed that my lowest number was about 50 and my highest number was about 90. So I said, okay, between 50 and 90 is about 40. And the amplitude must go up 20 and down 20. Yeah, Oscar, both of them will be up there. Any other questions about 95? Cool. Doesn't look like it. Let's do it. Thanks, Elmer. Okay, solving equations. Tan of theta plus root 3 equals 0. Then verify my results using a graphing utility. So I've got tan of theta plus root 3 equals 0. I'm going to isolate tangent. So I'm going to say tan of theta equals negative root 3. I'm going to say, okay, what's the inverse tangent? Theta equals the inverse tangent of root 3. I want to know for what values on the unit circle does tangent equal root 3? Let's pull up a unit circle for our viewing pleasure. Yeah, the 95, that would be with Desmos, Emily, for sure. Here's a nice unit circle. Okay, so where are we going to get just root 3 for tangent? So it looks like I want, oh, negative root 3. So I see I get it once here at 2 pi over 3, and then again at 5 pi over 3. No, Emily, there won't. And period here is pi. So set of values, 2 pi over 3 plus pi, union 5 pi over 3 plus pi. Richard, it's pi because the period is pi. Desmos. Tan of x. Period pi, right? See how it repeats every pi? Right, Richard? That's true, Ben. Tangent and cotangent both have periods of pi. And we want tan of theta plus root 3 to equal 0. So that happened at 2 pi over 3 and at 5 pi over 3. There it is. Oh, hey. So this is, I wasn't thinking. Oh, so this is theta equals 2 pi over 3 plus k pi, because this is just once a period. That's all it is. It only equals that value once every period. I could say this, but I don't need it. Not necessary. And this should have had k. Questions on 100 on the next section. Okay. Cool. 101. Sine of 2 theta plus 1 equals 0. That's what we're about to do, Richard. So sine of 2 theta equals negative 1. So I want the inverse sine, then 2 theta equals inverse sine of negative 1. I'm going to go back to my unit circle and say, when is sine going to equal negative 1? Well, that's only going to happen at, let's see, 3 pi over 2. So theta equals 3 pi over 4. And what's the period of sine of 2 theta? Well, period is 2 pi over, in this case, 2. So period is pi. So I can say theta equals the set of values, 3 pi over 4 plus pi k. Richard, I just looked at the unit circle. Said sine is the y value. The only place where the y value is -1 is at 3 pi over 2. See the unit circle? Do you see any other place where the y value, sine, is -1? Besides at 3 pi over 2? Do you see any other place where the y value, sine, is Cool. Solid. Fair enough. Okay, so then, and cosine is x. That is true, Richard. Very correct. Let's check on Desmos. That's also true, Richard. All true statements. Sine of 2 theta plus 1. Sine of 2x. Leslie, yes. There will be questions on that, like you just said. Williams, if it's not symmetric about the origin, then the symmetry is not odd symmetry. We only call odd symmetry symmetry about the origin. You could have symmetry about some other point, but that wouldn't be odd symmetry. And we want to know when this function equals 0. There it does at 3 pi over 4, and again at 7 pi over 4, and again at 11 pi over 4. There it is. We checked. Correct. Hurrah. No. Have symmetry that's either even or odd. If it's got symmetry about the origin, then the symmetry is odd. If it's got symmetry about the y-axis, then the symmetry is even. If it doesn't have symmetry about the y-axis or the origin, then the symmetry is neither even nor odd. But you could have symmetry about the point 0, 2. You just wouldn't call it odd symmetry. You just say it has symmetry about the point 0, 2. Function that used to be even and got translated to the right one could have symmetry about the line x equals 1. Doesn't have even symmetry anymore. It just has symmetry about the line x equals 1. Leslie, should we look at some finding maxima, minima, increasing and decreasing intervals, intercepts, and equations of asymptotes? Cool. Should we do it for this function? Jasmine agrees. Oscar agrees. Do you want to do it for sine of 2 theta plus 1? Or some other function? Let's do sine of 2 theta plus 1. Because we're on this page. And I've already got it graphed. For f of x equals sine of 2x plus 1. Let's see. Leslie had a nice list. It was, let's see. Oh, let's first do domain and range. Domain, all real numbers. Range, looks like 0 to 2. Domain and range, we did periodicity. Was, what do we say, pi, right? 2 pi over 2 is pi. So we know that the sine of 2x plus pi k plus 1 equals sine of 2x plus 1. Symmetry. This has symmetry about the point 0, 2. No, 0, 1. But that is neither even nor odd symmetry. Okay. Questions so far? Why is that neither even nor odd? Well, even symmetry is about y-axis, and odd symmetry would be about the origin, 0, 0. Does that make sense, Mary? So it's doesn't have symmetry about the y-axis. It doesn't have symmetry about 0, 0. So the symmetry is neither even nor odd. Fair enough, Mary? Hopefully. Anyway, let's see. We did domain, range, period, symmetry. Should we do maxima, minima? Maxima, I see pi over 4 and 5 pi over 4. So it looks like pi over 4 plus pi k, comma, 2. Minima are at 3 pi over 4 plus pi k, comma, 0. Exactly, Mary. It doesn't have symmetry about the origin, so it's not odd and it's not even. It has symmetry about the point 0, 1. It does go through the point 0, 1. That's a point of symmetry, but it doesn't have even or odd symmetry. The x-intercepts I'll do next because they're the same as the minima. 3 pi over 4 plus pi k, 0. The y-intercept is easy. That's at 0, 1. Do you have properties for tangent and cotangent? Yeah, I think you do. Yes, Emily? What else do we need? Oh, intervals of increasing and decreasing. So it's increasing on the interval from every minimum point, 3 pi over 4 plus pi k to a maximum point at 5 pi over 4 plus pi k. I'd be happy to, Emily. And it's decreasing from pi over 4 plus pi k to 3 pi over 4 plus pi k. Let's see, did I miss anything? No asymptotes on sine and cosine, right? That's all of it? Cool. So same thing with tangent or cotangent? Let's see, do we get any tangent or cotangent problems? Oh, here we go. Tangent of 2 theta equals 0. Perfect, let's do this one. So tangent of 2 theta equals 0. Inverse tangent and let's pull up that unit circle. And we know tangent is y over x, so I want to know when does y equal 0. Well, y equals 0 at pi over 2, and then again at 3 pi over 2. So 2 theta equals pi over 2, or 2 theta equals 3 pi over 2. So theta equals pi over 4, or theta equals 3 pi over 4. And what's the period here? Let's see. The natural period of the tangent function is pi, and pi over 2. Cool. So these two values are separated by one period. So that means I can express the entire solution set. Theta equals the set of values pi over 4 plus pi over 2 times k. And we can check on Desmos. When does tangent of 2 theta equal 0? Here it is at 0, 0, at pi over 2, and at pi. Did I make a mistake? Where's my mistake? Pi 2. Oh, I was looking at x equals 0. My bad. I mean, y equals 0. That's all bad. Sorry, everybody. So, starting from the top, tangent of 2 theta equals 0. 2 theta equals inverse tangent of 0. That should be at 2 theta equals pi, and 2 theta equals 2 pi. There's my problem. How did I know that the period was pi over 2, says Emily? Well, I know natural period of tan x equals pi, and I know that period equals pi divided by the b value. So in this case, the b value is 2. So I can say period equals pi over 2. So that's how I knew period was pi over 2, Emily. So then I was here. I said theta equals pi over 2, or theta equals just pi. I see that these two are separated by one period. So they don't both need to be articulated when I express in set notation. There we go. That's better. Now when I check on Desmos, that's what I see. Pi over 2, pi, 3 pi over 2, etc. Solid. Should we do all the properties for a tangent function? Yep. Sounds good. Thank you, Sophia. Okay, let's see. Domain and range. This is for f of x equals tan of 2x. We'll do. Domain. Y, oh, let's see. The set of values x such that x does not equal all the asymptotes. So where are my asymptotes here? It looks like pi over 4 plus pi over 2k. Because I have an asymptote at x equals pi over 4. And again at x equals pi over 4 plus so really 3 pi over 4. Cool. So there I got domain, which also told me about asymptotes, and range. Range for all tangent and cotangent functions is easy. The set of values y such that y equals all real numbers. Okay, domain range. Period. In this case, we already said it. It was the natural period pi divided by 2, which means tan of 2 times x plus pi over 2k equals tan of 2x. Symmetry. So this has symmetry about the origin, odd symmetry. How did I know the domain? Says Mary. Okay, so I saw that there was an intercept here at 0, 0. And I saw there was an intercept here at pi over 2. So I knew that halfway between pi over 2 and pi over 4 was going to be halfway between 0 and pi over 2 was pi over 4. So I knew that meant there had to be no x value at pi over 4. And I can see that here, right? 2 times pi over 4 would be pi over 2. Tangent of pi over 2 is undefined. Because pi over 2 on the unit circle is the 0.01. If I want y divided by x, that's 1 divided by 0, which doesn't exist. Can't divide by 0. If I plug pi over 4 in here, it's undefined. That's what makes it an asymptote on the graph. And then I also know that the period was pi over 2. So this problem is going to repeat itself every pi over 2 radians. Is that an okay explanation, Mary? Great. Cool. Symmetry was odd symmetry. I've got period, I've got domain, I've got range. What are we supposed to do next? We want to find maxima, minima, increasing, decreasing, intercepts, equations of asymptotes, right? So let's see. Maxima and minima. No maxima and minima. That's easy. Come on, Oscar. At least you have to agree that's easy if there's no maxima and minima. Whiner. No maxima, no minima. Never reaches a high point, never reaches a low point. No. If it was tan of 2x plus 1, then it would no longer have odd symmetry, Mary. No more odd symmetry. Well, because if we had tan of 2x plus 1, Mary, then the whole graph would be moved up 1. And then it would have symmetry about the point 0, 1, where odd symmetry specifically means symmetry about the origin, 0, 0. So if it has symmetry about 0, 1, that's not symmetry about the origin, 0, 0. It's a different kind of symmetry. It's symmetry about 0, 1, which we don't call odd symmetry. Odd symmetry is only symmetry about the origin. But luckily, we don't have that one. We have this other graph, which does have odd symmetry. Okay. Increasing, decreasing. Tangent is always increasing. Increasing. Just because it doesn't have odd symmetry doesn't mean that it has even symmetry. This graph had, if it had that plus 1 here, that would mean no even or odd symmetry. Even symmetry is only symmetry about the y-axis. Odd symmetry is only symmetry about the origin. Tan of 2x plus 1 would have neither symmetry about the y-axis or symmetry about the origin, so the symmetry would be neither even nor odd. It would not have even symmetry or odd symmetry. But again, we don't have that. We do have tangent of 2x, which does have odd symmetry. The tangent function is increasing on all intervals in the domain. And let's see. Asymptotes. At x equals, we already did this, but it was pi over 4 plus pi over 2k. Probably don't need to set notation there. Oscar, how much faith do you have in us? I would say 7. See? 7. Okay, Mary wants to know why is it pi over 4 plus pi over 2k? Well, the asymptotes, there was one here at pi over 4, and then there's going to be another one every period, and the period was pi over 2. So this is where the first asymptote was, Mary, and then the asymptotes happen again every period, and the period was pi over 2. Is that okay, Mary? Yeah, the period is always going to, the period is always going to separate asymptotes. Totally. You're going to have one asymptote every period on the tangent or cotangent function. On the secant and cosecant functions, you're going to have two asymptotes every period. Okie doke. Next one up. Sine of 3 theta equals 1. Hey, a nice sine function. So sine of 3 theta equals 1. Sine 3 theta equals inverse sine of 1. I go back to my unit circle. I ask myself, when does sine, which is the y value, equal 1? Y equals 1 at pi over 2. So 3 theta equals pi over 2. Yep, secant and cosecant is on the test. Yes, Emily. So theta equals pi over 6. I now need to find out what's the period of this function. It's 2 pi over b equals 2 pi over 3 in this case. So I'm going to say theta equal to the set of pi over 6 plus 2 pi over 3k. If I check it on Desmos, I've got sine of 3 theta, and I want it to equal 1. So here's sine of 3x, and here's y equals 1. I'll do left side function and right side function. and pi over 6. And again at 5 pi over 6. So that's 2 pi over 3 apart. And 3 pi over 2, etc. I'd be happy to do a secant or cosecant problem. Should we do one of those? Are we done with 104? Okay, doke. Here's one right here. Secant squared theta equals 4. Let's do it. So this one is like secant squared theta equals 4. This is another way of writing secant of theta squared equals 4, which means that I would like to square root secant of theta equals 2, or secant of theta equals -2, because the square root of 4 is either 2 or -2. Okay, looking at my unit circle, I know, well, let's say, rewrite it as cosine theta equals 1/2, or cosine theta equals -1/2. And cosine is x, so x equals 1/2 at inverse cosine of 1/2, or -1/2. So inverse cosine of 1/2 is at pi over 3 or 5 pi over 3. Or -1/2, which happens at 2 pi over 3 or 4 pi over 3. Sweet. So now we're wondering what's the period. And we haven't really had an opportunity to look at secant squared graphs. Secant squared x. But there it is. And you can see, beautiful graph, it only goes just up. It doesn't go down. It has a domain only greater than 1, because squared values are always positive. When you square a negative, it becomes positive. And it has a period of pi. So this graph has a period of pi. And we were interested in when it equaled 4. So I'm going to say left side function L of x, and right side function R of x equals 4. And there it is. Equals 4 at pi over 3, 2 pi over 3. I got those. 4 pi over 3, and 5 pi over 3. I got all those. So it looks like the pi over 3 and the 4 pi over 3 are part of the same period. So I don't need to really count this value, the 4 pi over 3, because I already got it. And I don't really need to count the 5 pi over 3, because I already got it. So I'm going to say theta equals pi over 3 plus, my period was pi k, union 2 pi over 3 plus pi k. Well, Mary, the natural period of the secant function is 2 pi. But here when I squared it and all of the values are now positive, the old secant function had some positives and some negatives. So the period was twice as large. But now that all of those negative parts of the graph have flipped upwards, the period has just become pi. So this secant squared function that I'm looking at here has a period of just pi. So this function has period pi. But just so we remember, the secant theta has period 2 pi. Okay. Do you guys want to look at like intervals of increasing, decreasing, maxima, minima, etc. with the secant function? Or would you rather move on to another problem? I'm not sure what you're asking for, Mary. Move on to another problem, or do maxima, minima, intervals of increase. Lauren says move on to another problem. Cool. The next ones were easy. They're just kind of fun Desmos work, right? Oscar's going to laugh at me when I say fun Desmos work. That's okay. I'm used to Oscar laughing at me now. We get left side function L of x, and it's 2x. And we got right side function R of x, and it equals 5 cosine x. And we just have to say where they meet. And there's only one spot where they meet. They meet right there, 1.11. Bam. X is approximately 1.11. 1. Emily, yes, the secant function has 2 intervals of increasing and 2 intervals of decreasing. Richard, is this exact problem on the test? That was pretty easy, right? Graph it, see where they meet. Pretty straightforward. I don't think something that easy is necessarily on the test. No. But it's worth understanding, right? That solving an equation just means where does the left side equal the right side? So the left side is, something that's not going to really meet the right side on very many spots, then it's easy. If the left side is going to meet the right side in a lot of spots, then it's harder. So Mary, you wanted to go back to the secant properties? Let's look at one more of these and then I can come back. So here's 2 of x, 2x equals 5 sine x. So 5 sine x. And it just happens here and here. and here. So x equals negative 2.125, x equals 0, x equals 2.125. There, Richard. Example problem where they meet multiple times. See how the blue one meets the green one in multiple spots? You are welcome. Okay, so we talk about last one again would just be, and then I'll do secant properties, Mary. So here's left side function is 2 sine x plus 3 cosine x, and it needs to equal the right side 4x. And that happens just twice. Oh no, just once. Right there at 0.867. Okay, so now back here. Mary, should we do it for just for the secant squared function we were looking at, or for a secant function? For secant, sounds good. So secant x. And let's transform it a little bit. Let's do, how about 2 secant of x over, or pi x over 4. That looks nice. Let's do that one. Okay. So f of x equals 2 secant of pi x over 4. Domain. Okay, so I'm going to turn this off, stepping by pi. Step by 1. So, Mary, you don't want me to change the amplitude? I was doing an arbitrary secant function, like you might have on your test. That's why. Is that okay? Okay, I won't change it. No amplitude change. Better? Domain is still the same though. It's x such that x does not equal every 4k minus 2. Right, we have asymptote here at x equals 2. Another one at, shoot. Why do I keep doing that? Another one at x equals 6, etc. And range. Looks like it goes from, so it's y such that negative infinity is less than y less than or equal to -1 union 1 less than or equal to y less than infinity. Symmetry, it's an even function. Symmetry about the y-axis. Domain, range, symmetry, periodicity. Period of this function is 8. So secant of pi x over 4 equals secant of pi times x plus 8 over 4. What else do we have to do? Maxima, minima, increasing, decreasing, intercepts, and equations of asymptotes. Okay. So maxima and minima. Let's get maxima. So the maxima, I can see there's one at 4, and then another one at 12, and another one at 20. So they're 8 apart. So the maxima are every 8k minus 4, comma, -1. And the minima are they're just every 8k, comma, +1. And intervals upon which I'm increasing and decreasing. Increasing. So that's where I'm going up. So I'm going up starting at a minimum point. So I know I have a minimum point at 8k. And I'm going to keep going up all the way to the asymptote. And the asymptote was at 4k minus 2, and there's an asymptote. But the next asymptote is always going to be 8k plus 2, right? Yeah. And then I'm going to keep going up from that asymptote to the next minimum. No, to the next maximum. 8k plus 4. And I'm decreasing. From a maximum point, which is 8k minus 4, all the way to 8k minus 2. And then again from 8k minus 2 to 8k, which takes me to a minimum point. I'm betting that's probably where some questions are. Anyone want me to talk more about that? What do you guys think? Have a good night, Richard. Good luck tomorrow. Well, if there aren't questions. Thanks. Yeah, it's tough for me to just pass out the final. I do need your good luck. I appreciate it. If there aren't questions, I will finish the problem though. Let's see. We did maxima. We can do no intercepts. Intercepts. And A. And asymptotes we already figured out. Thanks you, Brendan. Jasmine, I'm glad it was helpful. It's tough to ruin GPAs without luck. This is true. Emily, yes, that's absolutely correct. Well stated. Asymptotes, what did we say about asymptotes? We said 4k minus 2. For all integers, k. Yes, I agreed with you, Emily. The first part goes from minima to asymptote, and then from asymptote to maxima. That was beautiful. Exactly. What you said was great. All right, are we all done? What about the 0.01? What about it, Richard? Or Ryan? What about it, Ryan? Do you like it? Do you not like it? Is it important? Do we care about it? Tell me about the 0.01. It's a very nice point. Should we graph a point there? Just so we can see it even better? 0, 1. There it is. It's in green. Can't miss it now. Tell me about the 0.01, Ryan. Were you thinking it had odd symmetry about 0, 1? Or, I mean, symmetry about 0, 1, which wouldn't be odd? 0, 1 does look nice. You're right. But actually, you're noticing that it has even symmetry, right? It has symmetry about the y-axis. If I graph the y-axis here, I say x equals 0. That orange line is the line we have symmetry about, right? Yeah. Ryan was just hoping we got Christmas colors. Thank you, Sonny. Exactly. Cool. Any last things before I hang up? See you all tomorrow? Or Thursday, as the case may be? You're welcome, Ben. I don't know that it was our most successful episode, but we did get through a lot of the problem set, so that was impressive. You were welcome, Lauren. Have a good night. See you tomorrow. Wait. Mary says wait. What do you want me to wait for, Mary? You'll do fine, Lauren. You are welcome, Sonny. See you on Thursday. Definitely in the top 3. Thanks, Ben. See you, Ryan. Mary, what am I waiting for? Richard, you're doing great. Mary, I am going to do word problems. Yes, there will be word problems on the test. There might even be a word problem that looks a lot like that word problem. And there might even be a word problem that looks kind of like that word problem. You are welcome, Emily. See ya. I don't know who Lorna is, Richard. But I'm glad that you're going to do better than Lorna. You are welcome, Richard. See you tomorrow. It's going to be a test on everything we've done this quarter. Mary, that's all I can tell you. But it doesn't seem like you really have any more math questions, so I think I'm going to go. Tomorrow or Thursday. Have a good night. Goodbye.